doing a substitution in a definite integral is almost exactly the same as doing a substitution in an indefinite integral. The only thing you have to remember to do is to change the bounds. So for example, in this case, if we choose u to be minus sine 2t, then just like with a regular indefinite integral, we would calculate what du is. Let's see, the derivative of 1 is 0. The derivative of sine is cosine, so we'd get negative cosine of 2t times the derivative of what's inside times dt. And that means that negative 1/2 du is the same thing as cosine 2t dt. So we're almost ready to do our substitution. We just have to figure out what the bounds should be. Now, in this original integral, we have this variable t, and we have partitioned the interval from 0 to pi fourths. We're going to change to a new variable u. So this is our interval in t. What we're going to do is to create a new interval in u, and we want to know what are the starting and ending points for that new interval that applies for the new integral. Well, we can just look at where does our substitution take our two endpoints. So if we look at 0, the sine of 2 times 0 would be 0, so we get 1 minus the sine of 0, which is 1. So 0 is actually being moved over here to 1. Now pi fourths, the sine of pi fourths, let's see, 2 times pi fourths is pi halves, and the sine of pi halves is 1. So we have 1 minus 1. So when you plug in pi fourths for t, you find out that u is equal to 0. So what's happened here is every point, let's see, 0 was mapped to 1, and pi fourths was turned into 0. And every point in between is just going to end up at some location in between here. So the new bounds on our integral should be from 1 down to 0. That's because the original lower bound was 0, and 0 got turned into 1. So that will be our new lower bound. The original upper bound was pi fourths. That got turned into 0, and so that 0 will be our new upper bound. Okay, so when we go to actually do this conversion here, 1 minus sine 2t, that was u, so we get u to the 3/2. And then cosine 2t dt, that's equal to negative 1/2 times du. And then our new bounds, 0, the substitution, which tells you how to turn t values into u values, said the lower bound became 1. And the upper bound was pi fourths, and so using our substitution equation here, if we plug pi fourths in, we got 0. Now we can finish off pretty easily here. I'm going to pull out this negative 1/2 and integrate from 1 to 0 of u to the 3/2 du. If it bothers you to have a small bound at the top, you can remember our property of integrals that lets you change the order of integration, so it lets you reverse the bounds. It just puts in an extra negative sign. So by switching the bounds here, that's going to put an extra negative in here, which is actually kind of nice because that negative will combine with this negative 1/2 to make positive 1/2. And then we have the integral from 0 to 1 of u to the 3/2 du. Now that's just a power function because the exponent is constant, so I know that it's going to go up to be 5/2. Let's see, so we'll need a 2/5 downstairs, and we already have a 1/2. So we'll have to evaluate that between 0 and 1. Let's see, so we have, for our antiderivative, actually 1/5 u to the 5/2 between 0 and 1. Well, when you plug in 1, the square root of 1 is 1, and then if you take 1 to the 5th power, it's still 1, so we have 1/5 minus the square root of 0 is 0, and 0 to the 5th is 0, so we have minus 1/5 times 0, which is just going to be 1/5 for our answer.